Hi everybody, and welcome to a new video. Today we will explain the acceleration phase of a rocket, usually known as rocket equation. Rocket operation. The orange part represents the fuel of a one-stage rocket. The movement is based on Newton's third law of motion. Every time the rocket expulses exhaust gases backwards, its mass decreases a certain amount of mass, and its speed increases a certain amount of speed. V sub E is the speed of the exhaust gases relative to the rocket, and it is always the same. As you have observed, the mass of the rocket decreases over time, making it easier to increase its speed along the way. If we assume the rocket is in zero gravity and there is no air around it, this is the only mechanism that takes place. Let's start with Newton's second law of motion, where the summation of F are the external forces over the rocket, and the vector P is the linear momentum of the rocket. With zero gravity and no air, this means analyzing one of these events, since the movements are rectilinear, we can write it. Using now the previous deduction from Newton's second law, operating this expression, if we take into consideration that fuel burning is continuous and each of these steps is actually infinitesimal, minuscule, we can assume that the mass decrease and the speed increase are tiny. The product delta m delta v is, therefore, negligible in comparison to the terms v sub e delta m and m delta v. At this point, we need to mathematically define the terms delta m and delta v. Let's start with delta m. From the previous diagrams, it is the amount of fuel that is expulsed between T1 and T2, which is equal to T1 plus tau, and can be expressed as this is a continuous process. The time tau is as small as we want it to be, tau tending to 0, so we can do the following. Now we have to remember the definition of a derivative. In our case, with the function m of t1. If we take a look at this part of the expression, we can get the following equality. Looking now at these two equations, we can deduce as we stated before, in a continuous process like this, tau tending to 0 is fulfilled, so it results in, following the same process with delta v, we get in this case, both expressions match. And again, in a continuous process, tau tending to 0 is fulfilled and the final equality results. Now it's time to solve this and find the movement equation of the rocket. We have to reorder the equation in order to integrate and get a function v of m. We integrate between the initial point m0, v0, and a certain point mv. The result on both sides of the equation results. And finally, here it is. This is the rocket equation. With it, you can determine the rocket speed v as a function of its mass m, where v sub 0 is the initial speed, v sub e is the speed of the exhaust gases relative to the rocket, and m sub 0 is the initial mass of the rocket. It is always fulfilled that m is less or equal to m sub 0, and v is equal v sub 0 when m is equal to m sub 0. Let's plot it now. As you see from the formula, when the rocket fuel is burnt and m decreases, v increases. This effect is more accentuated once m is small, since it is easier for the rocket to gain speed for the same impulse. This equation supposes all the mass of the rocket is fuel, so when m tends to 0, v tends to infinity. Let's get an easier visualization. If the rate of fuel burnt is constant, we can write the mass expression as where c is a constant. Then we have and this is the rocket equation as a function of time. That's it. Hope you liked it, and see you in the next one.